last speaker before the break is Dr. Gerald Cleaver. Gerald earned his PhD in early universe cosmology and string theory at Caltech in 1993. He's a professor and the graduate program director of the Department of Physics at Baylor University in Waco, Texas, where he heads the early universe cosmology and string theory division of their astrophysics, space physics, and engineering research center. So I'll turn it over to Dr. Cleaver.
Thank you, Les.
Yeah.
Thank you for the opportunity to speak here. Let's see. Okay, yes, and my talk, it was a great intro. Thanks, Jeff, for preparing for this talk here. I'm going to talk about some research my students and I and research colleagues are working on, specifically with regard to wormholes. One thing about wormholes, we're going to talk about them, but it's not just like a given wormhole type. There's a wide range of classes. Talking about wormholes is like saying, I'm going to go get a car. You know, wide range, different models, different designs and all that. Some are more stable than others. Long history, as was mentioned. Some of the first people to work on were Morris, Thorne, and Yurtsever. There were actually a few people before that who were looking at them. There are a couple cosmologists who were working at them, but calling them drain holes. That somehow didn't seem to catch on as much. Those were a couple of papers earlier than the first Morris, Thorne, and Yurtsever by about 10 years. But even Morris, Thorne, and Yurtsever had not studied those. So in the end, the Morris et al. Papers actually were copying some of the original work on drain holes on that. But there has been a wide class. What my students and I have been looking at a range of properties of wormholes. In fact, I want to introduce my research group. I've three adjunct research professors. Eric Davis, I'll make mention later on to some research that he's doing. Ahmed Borzo, Jeff Lee, and then my five current PhD students. The papers that I'm talking on now, most of it is going to be the dissertation work that Brandon Mattingly is going to be defending in a couple of months. And then Abhinash Kaur has been also working with it. Cooper Watson, and then also attending this talk with me is Matthew Gorbin and William Julius. They've been doing specific aspects of this. As Matt just said, his thesis will be on Casimir effect. Will has been working on a variation of wormholes in extra-dimensional space. He has been studying 5-dimensional wormholes and showing that it's actually possible to have a wormhole that appears to not need negative energy in 4 dimensions, but the negative energy shows up when you consider the a fourth compact spatial dimension. So that looks like one alternative to saying everything has to have negative mass or negative energy in our 3+1 spacetime. Again, the research I'm going to be talking on is based on 3 research papers. Curvature Invariants for Lorentzian Traversable Wormholes, which is under review at Universe Journal, and 2 others that are in preparation for submission. Wormholes have become more in vogue recently because of a couple papers that have been released, one of which came out in August, that claimed to present step-by-step instruction for building a wormhole. This hit the news and all. And again, this was one of the papers that have argued recently that in place of negative mass, one could use cosmic strings. Basically, the idea in this paper that caught on was starting with 2 black holes or black hole wormhole, connecting their singularities via wormhole, and then stabilizing the wormhole by cosmic strings going through the mouths and throat. And so we've been looking at that. That caught attention a lot. What we've been doing is making the assumption of the wormhole as some type of stable wormhole existing. We're assuming it's negative energy, cosmic string, whatever's needed to stabilize. And what we've been doing is analyzing the curvature in these black holes. We're examining a particular class that Morris, Thorne, Yurtsever, and Matt Visser are claiming to be stable, traversable. By traversable, they basically mean that an object, including life form, can travel from one end, one mouth of the wormhole, through the throat and out the other end in a finite time and survive. That means specifically meaning that the gravitational fluctuations, the gravitational fields, the curvature is weak enough that there is nothing dangerous. And so this is particularly what we wanted to examine and have done our papers on, the traversability of these black holes by examining the curvature. What we're looking for is low enough curvature that they're basically safe. And by curvature, we want basically minimal variation from flatness for the curvature. So to do that, what we were looking at, we have to go back to, as Jeff was talking about, we examine the Einstein metric for the gravitational fields through these black holes. They can get very complicated. There's a wide range of black holes, excuse me, not black hole, wormhole, wide range of wormholes that we were investigating. And so we worked out a mathematical program that allows visualization of the space-time gravitational curvature. And we've just, as we expected, having a visual representation is much better than just seeing the equations and trying to figure out how bad the curvature is, or how good. And so I'm going to talk about three wormhole metrics: Morris-Thorne, thin shell Schwarzschild, and exponential metric. And again, as I said, there's a wide range of possible types of wormholes, and it's not just one. It's like all the various car companies and the models of cars each one makes. So what we're doing. Then I'm going to go on, if there's time, and look at what was initially thought to be a possible wormhole, and then turned out not to be. The metric actually disclosed not a wormhole, but hyperdimensional space-time with circular bounded directions. And then if there's time, I'm also going to show how the process that we've been doing for analyzing curvatures can also be used to analyze things such as Natario warp drive, and to get an understanding of the space-time curvature that something like that would produce, and contrast to some of the papers written on Alcubierre and Natario warp drive. We've discovered that if advanced technology, alien race actually were able to use this, there would be some signs of able to detect ships using Alcubierre or Natario warp drive. We've discovered that from the curvatures we're seeing that very, very high frequency gravitational waves would be produced by it. Right now they're not. They are too high frequency to be detected by LIGO or something like that. But nevertheless, future gravitational wave detector could possibly detect the gravitational waves produced by something like Alcubierre or Natario warp drive. What I'm going to be showing are called curvature invariants. We're going to be using Einstein relativity. We look at the gravitational metric G mu nu and the functions that come from it. Most famous is the Riemann tensor, which is formed of the connection which is derivative. First order, the connection is derivatives of G, and I'm using IK to represent 0 for time, 1, 2, 3 for the spatial directions. We have the connection which is formed a derivative of G and multiplied by G, Riemann tensor, which is functions of the connection, so therefore it's first and second derivatives of G, has 4 indices then, the original 2 plus 2 for the derivatives. Ricci tensor, which is a trace of the Riemann tensor, and then from the Ricci tensor one forms the Ricci scalar. There's also something known as the trace-free Ricci tensor, which just, if it's a metric 2 by 2, subtracting out, making it tensor trace-free. Riemann tensor, which is formed from, the Weil tensor, which is formed from the Riemann tensor, and with producing some anti-symmetrized terms, which only occurs when there is torsion in gravity. Not going to discuss those anymore, other than knowing that they're tensors coming from derivatives of G. Overall, if we go back and look actually at the number of independent degrees of freedom in the Riemann tensor, it's actually 4 times 4 times 4 times 4 indices, but overall there's only 14 degrees of freedom, which means that if any given point in space, to understand the curvature at that point, we actually would need 14 scalar degrees of freedom. Gets complicated. One of the things we were showing was that for most wormholes that have been considered, the symmetry rules, when enforced, reduce the number of independent scalar degrees of freedom, defining the spacetime curvature to reduce from 14 to 4. So what we did was analyze these 4 different independent degrees of freedom of the Riemann tensor that can be expressed ultimately simply as scalars. And the people who had worked this out and allowed us to use the arguments to show that we can go from 14 to 4 degrees of freedom are Carminati and McClanahan. So the 4 degrees of freedom that we used were referred to as the Carminati and McClanahan, or CM, invariants. And the 4 that we'd worked with, we're going to note, one is the Ricci scalar, capital R, and the other 3 we denote as R1, R2, and W2. Doesn't matter exactly the equations or what they are, other than that knowing that these 4 degrees of freedom, the scalar fields, fully define the curvature of space and time for any of these wormholes, or anything else that satisfies the symmetry constraints to fit into this class, as did the other things that, if I have time, I'll talk about. And all of these, the class that they fit into are known as the Petrov type, which I don't have time to go into, of class B spacetimes. Won't go into that either, unless somebody wants to have some fun reading about it afterwards. Again, we're going to start with Morris-Thorne wormhole. And Jeff showed us examples of a spacetime metric, which this is. This is the invariant distance, as Einstein's equation, that has the components. If I was moving in time, the warping of time as I move is taken into effect by the G00 factor, exponential here. Moving if solely in the radial coordinate, this factor tells me the warping of the radial outward, and these are the angular coordinates. And here we have angular symmetry, so I'm not having any warping along those directions. The degrees of freedom here, there were 2 degrees of freedom in this metric that Morris and Thorne were looking at. One is known as the shape function, B, appearing here, and the other as a redshift function, phi. And phi, this coefficient of time, the warping of time, indicates how, as I'm moving purely through time, how time is being warped. In this case, it would be how time is being warped as I move through a wormhole from one mouth through the throat and out. We made some simple assumptions, the type that we were looking at in particular. We simply said there's no warping of time in it. We chose a consistent redshift function equal to 0, so e to 0 just factors out as 1. Shape function, we showed there are geometric and physical constraints on the form of it, and we picked one of the simplest, again, to look at to denote. So we put those in. We form Riemann scalar R1, R2, and W2. There we go. Get complicated. Again, looking at that doesn't tell us much. I don't learn much looking at it. However, I'm going to get a plot of that, a plot of those, each of those, and that tells me quite a bit more. You saw R1, R2, all complicated. But instead, same information contained right there in the mathematical plot for that. And this tells us that these are functions of how the space-time is being curved. And what's interesting is these are 4 independent types of curvature. Ricci scalar, R1, R2, and W2. And it shows how, and these are all functions of the distance that we're moving in and the overall minimum radius of the wormhole. And the minimum radius is always right at the center of the throat. And so what this shows us that as long as, for Morris-Thorne wormhole, as long as the radius is big enough, we pretty much have flat space-time curvature going in. It's really stable. We don't have to worry about being torn apart going through the wormhole. And whatever radius we're at, we just go out. This is a radial measure. As long as it is big enough, there's not much curvature. You get a really, really small throat. Yes, there's a divergence in all 4 directions. 3 positive in whatever type of curvature is. What we don't know is exactly what type of curvature is. It could be a stretching, it could be compact, it could be rotational, it could be stress on it. We don't know, but we could work it out. We just know that these 4 types of curvature. Main thing is that none of them diverge. So this was a nice demonstration that the Morris-Thorne wormhole was stable. 4 different types of curvature, but none, as long as the throat is big enough, none that would endanger anyone traveling through it. Thin shell Schwarzschild wormhole. This was an interesting type. What's happening here is the type of wormhole is we basically assume we have a black hole. We have the event horizon around distance r0. We have a black hole here. What we're actually going to do is cut space-time by the first black hole. We're going to cut space-time right at the edge of the event horizon. We're going to cut the other one right at the edge of the event horizon, and then form a connection between the event horizons, which gives us a good minimum radius, r0, again, and minimum throat, space is contracting, event horizon. We just cut and glued them together. And that has become known as the thin shell Schwarzschild, as in Schwarzschild black hole here. And again, this is the metric. This is the G00 term, the G11 term, and flat along spherical symmetry. Nice and simple here, again, in contrast to the other different model. Ricci scalar, R1, R2 are all 0. W2 is the only non-zero one. Complicated. Again, can't tell much. I don't learn anything looking at this. We won't study it. But we get a plot of it. And that's it. And again, it shows that this wormhole is nice until we get close to the event horizon distance, which we pasted together. Very stable. So you have a large enough R0. No curvature again. It's nice. Let's see. And then the last one we looked at, this was the thin shell Schwarzschild. The last one we looked at is a little more complicated one known as the exponential metric. Again, it's like we've been looking at 3 different auto companies' versions of wormholes. This is another one and probably the most complicated we see, but still fairly simple. The gravitational coupling G mu nu are exponentials. And here this is the time curvature, and this one curves the radial and angular coordinates. You get non-zero R, R1, R2, W2. And they're most interesting too. Here we see when we look at the curvature, we have, starts out as near flat, then goes negative curvature, then positive, reaches a finite peak. This is even in the limit that R was to go to 0. Still stable. You can see here, again, same type, sort of inverted curvature for R1. Goes up, positive curvature, then negative, and then balances out. Here, same type of thing, sort of inverted. Very interesting. Shows you how different the types of wormholes can come. And that was the last one. Then we also were studying one type of what was thought to be a wormhole for quite a while. Discovered and discussed by Levi-Civita, the famous Italian mathematician. What he was considering was producing artificial gravity from a uniform magnetic field. And then it was studied more recently by Claudio Macconi, the IAA chair of the permanent SETI committee. And as an aside, he was also examining wormholes, and he was theorizing that the Levi-Civita spacetime metric could be considered magnetic or electrically induced wormhole. And then more recently, there was a paper out by Hal Puthoff, my colleague Eric Davis, and Macconi himself. They later proved that the metric that was produced by this actually describes a spatial hypercylinder with a positive dependent gravitational potential. In fact, it wasn't a wormhole. If you want to think of it as a wormhole at all, it's saying that one of our spatial directions was periodic, and that the wormhole basically, you never came out of the wormhole. It's basically a permanent infinite wormhole describing space-time. Nevertheless, we worked to see what that type of supposed wormhole induced by a magnetic field look like. Fairly simple metric, but again, we saw the periodicity in space-time in change of coordinates of it. And then also we ended up 3 degrees of freedom, because one of the 4 ended up being 0 here when we computed them. We showed that some of the plots actually produced divergence of the curvature of this type of supposed wormhole, but there were also constraints of some of the degrees of freedom in there, the constants in the parameters in the metric that could produce no singularity under certain conditions. Basically here, this was an odd metric, odd curvature that looks like a bowl, given that the constraints eliminated the singularities, and it can evolve and flip over for any of the other the 3. This is the one. This is where if for R, different parameters of the kappas that I showed for a second, you could change. You can have divergence or not. You can have it disappear, depending upon what some of the parameters, the values that were chosen. And this is just evolution if the parameters were varying themselves. And again, the value of what can come out of visualization of these curvatures, rather than, again, looking at the essentially meaningless equations on it. Lastly, it looks like there's still a few minutes to talk about it, we applied the same thing to investigating the Natario warp metric. And this is a variation of a Alcubierre metric, and I want to review what these metrics did. These metrics describe space-time warps that could theoretically allow effective superluminal travel globally within the framework of GR. And Alcubierre, back in 1995, worked this out by generalizing the physical idea of inflation, where space-time itself was expanding faster than the speed of light. And what do I mean by that? That was the stage where we had exponential inflation. And again, when I talk about expanding faster than the speed of light, even now, if you go the further away 2 points in space are, the faster their effective velocity of repulsion. But it's not the objects that are moving away, it's space between them. And nothing forbids space from expanding faster than the speed of light. And so what Alcubierre wanted to do was, okay, say, I'm going to take advantage of that. Let's see if, what he asked is, can I form some bubble in space-time and produce the physics that would allow that bubble to travel faster than the speed of light with regard to the space around it? And he found a metric for which that was true. What he showed he had to do, as Jeff was mentioning, is you have to throw in negative energy for it. And what he showed was that what Alcubierre worked out is the mathematics of the metric of space-time that has a negative cosmological constant, negative vacuum energy in front of this sphere, positive vacuum energy behind it. Positive means space is going to be expanding behind the ship. Negative vacuum energy in front means space is going to be shrinking. And if you correlate the shrinking rate in front, the expansion behind, basically, and a ship in the center, what you actually have is like a ship traveling on a wave, shrinking of space continually in front, expanding behind. And so, and again, you can have expansion and shrinking faster than the speed of light. So what that appears, if you're outside of this bubble looking on, this warping of space-time appears to be propelling this bubble at up to luminal speeds and then superluminal too. And so Miguel Alcubierre became very famous for the paper that he published back in 1994-95 for this then. There were some issues, and again, there's been probably 40 papers written on the Alcubierre warp drive, and I have a couple out too with my colleagues, pointing out some of the technical issues and also some of the theoretical issues. Several tried to improve on the Alcubierre warp drive, one of which was Natario. And he claimed to overcome the obstacle of the huge amounts of negative energy required for stabilization of the Alcubierre warp drive. Whether that's true or not, I'm not going to argue. Instead, what my students and I did was try to get some idea of how space-time was being warped, given that the Natario warp drive actually worked. And so we did what we did. I'm not going to go through the metric, but it does include something called the shape function, which was like B before. And we examined for the standard shape function that Natario was using what happened. There you go. I'll skip to ahead. Only a few minutes left. And again, the nice thing we discovered was that the metric fit into the CM constraints again. So we only had to examine the 4 scalar degrees of freedom to get an understanding of what the warping was looking like for the Natario, which was nice. Again, reduced from, surprisingly, from 14 to 4 for one of these warp drives too. There were a few degrees of freedom in the Natario warp drive. Skin depth, basically the thickness of the shell, separating the flat space inside to flat space outside, and the curvature between that had effective positive curvature behind, negative in front. The size of the warp bubble itself, the acceleration rate of the bubble, and the time elapsed. Our group looked at all of those to see what the gravitational waves and curvature would look like given this was physically obtainable. Discovered some interesting things. This is a plot. Sigma is the thickness in a given metric unit. R, not Ricci scalar here, but R being the radius of the shell, and A being the acceleration. And what we see here is the bubble is traveling forward along in this direction. And what we see is this was t equals 0, t equal 1 second, 10 seconds, 100 seconds at an acceleration of just 1 meter per second squared. What we see is, again, there's the huge warping right center of the bubble. The bubble is safe and flat right in here, but there's this line. And as it starts accelerating, you see a real warping of space right along the center of the shell. Again, we're moving forward like this in time. And you go from one curvature, peak, and the opposite curvature going like that. And you see the same pattern in all. And what you really see is that as the ship is accelerating, the bubble is accelerating, the warping of space halfway through is severe. Those are going to produce high frequency gravitational waves. And we took graphs of other parameters too. Plot of varying R. Radius didn't have much of effect. It was just a scale factor that didn't change things significantly. As it shows there, the same basic effect of this huge warping of space-time, splitting the shell or the bubble of the Alcubierre. And this one, we also found out that the thickness of the shell didn't play much into the various warpings. This one plots for the invariants for, let's see this again, standard radius, 100 meters, constant acceleration at one time, looking at all 4. And you can see there is some real warping of space-time, peaking, almost singularity sheets in the front and back of the ship. Again, we're going forward at that angle there. And this shows all 4 R, the Ricci scalar, R1, R2, and W2, the 4 warpings, severe. So we learned a lot, and these warping effects are contrary to what Natario or Alcubierre had expected. So we've learned a lot looking at these. And I'm going to finish up with that. Curvature invariant summary. Just the basic idea that going back and looking at writing a Mathematica program to visualize the different independent degrees of warping that one can expect from wormholes or other means of warping, of warps of space-time. I think we've learned a lot, and we plan on just carrying this through to other warped space-time solutions.
fascinating, although I have to say I'm not entirely sure if I know what it means. What bothered me about your curvature invariants for the Natario is that they don't seem to be decaying to asymptotically flat at infinity. So they don't look like they're physically real.
Let's see, I would, at infinity, they are. We're seeing, again, we're in limited space. If we went out radially, we would, if we went far enough out radial at 90 plus and minus 90 degrees, we probably would have seen them cut off. These do flatten out.
Yeah, certainly.
But again, I would agree with you. That's what I'm saying. There is high curvature right here, but probably if we did go out far enough, it was taking us a lot of time to get that.
Okay.
So I would expect you're right, and that's what I would expect, that these to curve downward to flat here.
Well, actually, that's I suppose, a question. When he constructed that space-time, did he put in the constraint that it's asymptotically flat?
No.
So it may not be asymptotically flat.
It may not be. This
so
is, again, what we were looking at is Natario's version. We went with the metric. So all I can say is all the other studies and curvatures we've done were what we were expecting. We expect our plots to be correct. This is just the metric he was using.
Interesting.